We're going to take a quick look at the periodic table. This is just our first of many examinations of the periodic table. First of all, it is arranged by atomic number. So every single atom on the periodic table has a certain number of protons in its nucleus. The number of protons is called the atomic number, that is Z. And we arrange them on this chart from low to high. So the number is written above here. So there's 1, there's 2, there's 3, there's 4, there's 5, there's 10. And so you can see that we're arranging them from left to right. So 11, 12, 13, 14, 15, 16, 17, 18, and so on. So they're arranged by atomic number. If you notice, there's no gaps. If there were a gap, there would be an undiscovered element. The horizontal rows on the periodic table are referred to as periods, and we can see this is the first period, the second period, the third period, and so on. The vertical columns are referred to as groups, so these are groups 1 and 2 and 3 and 4 and 5, all the way to group 18. And so our textbook actually uses groups 1 through 18 now. This is actually the modern way of doing it. But until recently, we used to actually refer to using A's and B's. And so we would say the left-hand 2 columns and the right-hand 6 columns were part of the main groups. And these were numbered 1A and 2A. Let me switch to a laser pointer. 3, 4, 5, 6, 7, and 8A. And these were the transition metals, and these were number 2. We normally didn't point out these numbers, but you can see they're 3B through 8B, and it's interesting we come back and do 1 and 2B here. Now the modern way to do it is just 1 through 18. We'll probably still refer to 1A, 2A, 3A through 8A on the exams, but you should be aware this is sort of falling out of style. You'll also notice as you go across the periodic table, when you get up to element 57, which is lanthanum, then there's a gap. It goes from 57 to 72, and the reason for that is that these rogue elements here have been sliced out and placed underneath. So these are called the inner transition metals. So let's just write that out. These are the inner transition metals. Okay, and in the center, these are just the regular transition metals, or transition elements, I guess. So the left-hand side we said is the main group, so we've got main groups here, and we've got 6 main groups on the other side as well. We've got the transition metals and the inner transition metals. This is actually considered the short form periodic table, so I'm going to go ahead and show you the long form one. And this is the long form one, I think, from Wikipedia. So you can see what we've done here is we've basically taken these elements here in the short form periodic table and cut them out. So imagine you take a pair of scissors and you make a snip along here and you make a snip along there, and you basically pull this down and then you move these sides together, and that gives us the short form periodic table. Otherwise your periodic tables would have to sort of fold out, or they'd have to be printed half the size. There's a lot of different ways to write the periodic table, and we like the short form. It's quite convenient. It's not perfect, but it's pretty darn good. If we look at groups 1A, what we find is that group 1A, all the elements behave very similarly to each other. So lithium, sodium, potassium, rubidium, all of these are referred to as the alkali metals. And what we find is that in general, the groups have similar properties. So the groups have similar chemical properties. And the alkali metals all have similar properties, and one of the most famous ones they have is that they react violently with water, and they actually form hydrogen gas, which the reaction gives off a lot of heat. It often ignites, and you get a big boom, and they produce a solution that is an alkali. And an alkali is simply a base that is dissolved in water. So a base is something that can neutralize an acid. So when you add lithium or sodium or potassium or rubidium to water, it reacts violently, and the resultant solution is capable of neutralizing an acid. It's called an alkali. Group 2A, I'm going to write it like so. These are the alkaline earth metals. So it's very similar to alkali. Make sure you can remember the difference between them. Earth, because a lot of these elements were found in minerals or earths. Earths were thought to be basically indestructible. It turns out that you can destroy them and you can break them down, but you have to heat them to very high temperatures and pass electricity through it to actually get these alkaline earth metals out. And so when electricity was first discovered, a lot of these elements basically popped into existence because what people had to do was melt their sample of earth, pass electricity through it, and you make magnesium and calcium and strontium. And they are violent in terms of their reaction with water, but not as violent as the alkali metals. So they react with water slightly less violently than alkali metals, and they also produce an alkaline solution, which is to say a solution that is capable of neutralizing an acid. Now notice I'm going to write solution SOLN just because I'm lazy. Now if we look at a couple more groups of the periodic table, we're going to pick on 7A, or group 17 in modern terminology. This is the halogen group. So these halogens are so called because they are the salt formers. So Gen is former, Hal is salt. And if you look at fluorine and chlorine and bromine, these all react with sodium to make sodium fluoride, sodium chloride, sodium bromide. Sodium chloride is regular table salt. Sodium bromide is sort of the table salt which has extra bromine in. And sodium fluoride is what's sometimes found in toothpaste. But they're all white, crystalline, salty flavored things. And lastly, is group 8A. These are the noble or inert gases. They are unreactive. They do not combine and form compounds unless you use extreme temperatures and reaction conditions, or you use elements that are incredibly reactive like fluorine. Most of the time they're completely unreactive and inert, and they don't do anything at all. We can also look at some other things with the periodic table. We see that the whole left-hand side of the periodic table, with just a few exceptions, consists of metals. And metals are things that are shiny and conductive in terms of both heat and electricity. They're malleable. They can be sort of beaten out to make sheets. They're ductile. They can be pulled through narrow openings to make wire. And then on the right-hand side, we see elements that basically are the yin to the yang. So these are the non-metals. They basically are the complete opposite of the metals. If they are solids, they tend to be dull rather than shiny. They tend to be very poor conductors of heat and electricity, with a few exceptions. Poorly conductive, I guess. They tend to be brittle. So if you hammer on them, they tend to crack. If you take a diamond or something and hammer on it, it doesn't make a sheet of diamond. It makes a bunch of little tiny diamond crystals because you've broken it, and you can't pull it into form a wire. And you see elements that are sort of colored in purple here, and these are referred to as semi-metals or metalloids, which always reminds me of hemorrhoids, to be honest. And they're sort of in between. So the classic example is an element like silicon. So silicon is an example of an element that is quite shiny, just like a metal, but it's also incredibly brittle. If you hit it with a hammer, it tends to break. And in terms of conductivity, it's a little bit conductive. So it's not nearly as conductive as metals, but it's a lot more conductive than non-metals. It's sort of in between. And the silicon in silicon chips is typically doped with elements to improve its conductivity, because by itself, it really is a semiconductor. It really doesn't conduct electricity terribly well.